Bismillahirrahmanirrahim. Welcome everybody in this online lecture. So we are discussing about the unsuggested problem solving technique. And we are discussing about the LAM system, and if LAM system applicable, then first we need to calculate Bart number. If it is less than 0.1, then you can use it. If it is more than 0.1, then you cannot use it. So if it is more than 0.1, then LAM system not applicable. Then use approximate solution technique, and this technique is also valid if f0 Fourier number greater than 0.2. Fourier number greater than 0.2. If these two conditions satisfied, then approximate solution okay. So last lecture we discussed about the technique of about approximate solution. So we will do an egg 5 centimeter diameter is initially at uniform temperature. So egg you can consider as a sphere, 5 centimeter diameter. Diameter is 5 centimeter. So R0 will be 2.5 centimeter per meter. Is initially at a uniform temperature of 5 degree. Here this, and is dropped into boiling water. So boiling water temperature T alpha. Taking the convection heat transfer coefficient H. This determine how long it will take for the center of the egg to reach 70 degree. Center. So this center temperature 70 degree. How long time it is required? So this is the question. K given, alpha value given. So first find the Bart number. Bart number equal to C by K. So it is spherical 0 by 3 by K 1200 R0 by 3 0.025 K is 0.627 0.627. How much it is? $15.95, so is greater than 0.1. So LAM system not applicable. So try approximate solution. Then new part number will be HLC by K. H is 1200, and in this case the LC will be R0, right? Only R0 divided by K. 1200 and 0.025 divided by K, 0.627, equal to 47.8. 47.8. So around 48, right? Here. So your C1 will be around, if you go in calculation, then 1.99 around C1, and Zion will be 3.075 around. And the equation that we have when R equal to 0, SPR, this is the equation. We will use this equation, T minus T alpha, T minus T alpha equal to C1 it is 0. So T is 70 minus 95 by 5 minus 95, C1 1.99, 0 minus 3.0755 square F0. So F0, from here you can calculate the F0. F0 equal to, can you calculate? I got here 0.0209. So which is greater than 0.2, so it is satisfied, right? Satisfactory. Approximate solution satisfactory. F0 equal to 0.209. F0 equal to alpha T by S square. LC square mean R0 square, right? 0.025 square divided by alpha. Alpha equal to 0.156 10 power minus 6. 0.151 minus 6 meters per second. So you will get 865 second. So this means 14.4 minutes. So after 14.4 minutes, the temperature of the center of the egg will be 70 degree. Any question? Is there any question?
Clear, doctor.
So we have another method in this chapter. We will discuss finite difference method. But finite difference method we already know in chapter 4. But in chapter 4 we didn't include time. But here we will include time. So if you want to include time, then storage term, rho C volume dt by dt. So storage term we need to add here, and then here actually there is time dt by dt. Temperature change with time. So this dt by dt we can write in terms of finite difference technique. T p plus 1. P plus 1, that is the future and P that is the previous temperature or existing temperature divided by delta T. P plus 1 minus T plus 1 minus Tp divided by delta T. And always we want to find the new temperature after certain time. Always we want to find the Tp plus 1. And this is explicit techniques. We'll use the previous time or previous temperature for predicting or for determining the future temperature. So let's do one. So if you see the different cases here, interior nodes, this is the equation. On node at interior corner with convection, like here. Node at plane surface with convection, like in the corner here. Node at exterior corner with convection, like this here. So how to write the node equation for this kind of scenario? You already know from chapter 4. But chapter 4 we didn't include time. Now we include time, then let's see what happened. Let's see the interior node. So case 1, interior node. So this is 0, like this node. So 1, 2, 3, 4. So what we did, we took a control volume here and we say all energy going there. Q4. So Q1 plus Q2 plus Q3, Q4 equal to rho Vcp dt by dt. We want to include time here because we are considering unstable or transient conditions. So what is Q1? Same as before that, you know. So K delta y into 1 by delta x T1 minus T0. Q2 K delta x into 1 by delta y T2 minus T0. Q3 K delta y into 1 by delta x T3 minus T0 plus Q4 K delta x into 1 by delta y T4 minus T0 equal to rho Cp volume delta x delta y into 1. T0 P plus 1 minus T0 P divided by delta T. And all the temperature here P existing. All these are existing temperature P. So P. And our aim is to find T0 P plus 1, the next, the future temperature after certain time. What is the temperature of T0? So that is T0 P plus 1. And whatever temperature here are existing temperature, or you can say previous. So you can say calculate the future temperature based on the previous temperature. So you can simplify this. So K T1 P T2 P plus T3 T4 P minus 4 T0 P rho Cp delta square T0 P plus 1 minus T0 P T1 P plus T2 P plus T3 P T4 P minus 4 T0 P equal to rho Cp delta x square by K into delta T. K by rho Cp, that is alpha. So K by rho Cp mean alpha diffusivity. So until now, okay.
Yes.
So F0 we can write alpha delta t by delta x square delta square. This is the finite difference form of F0 alpha delta t by delta x square. So 1 by F0. So multiply F0 to left side. F0 So rearrange this equation, we want T0P plus 1 equal to T0P plus F0 T1P plus T2P plus T3P T4P minus 4 F0 T0P T0P 1 minus 4 F0 plus F0 T1P plus T2P plus T3P plus T4P. We want to calculate P plus 1 based on the existing temperature. So this is the equation that we got, and we got the same. You see, F0 if it is 1, 2, 3, 4. If it is 0, 1, 2, 3, 4. 1 minus 4 F0 T0 P. So same equation. Same equation I got. Now if you look at the here, stability criteria. So stability criteria, what is this? Stability criteria. So your solution is stable when you say your solution is stable. For example, if I say find temperature after 60 seconds. After 60 seconds. So what would be the delta T? So delta T could 10 seconds. So how many iteration? 6. 6 iteration. After 6 iteration, you will get the 60 second. If you say delta T is equal to 15 seconds, 4 iteration. Delta T equal to 20 seconds, 3 iteration. Delta t 30 seconds, 2 iteration. Delta t time 60 seconds. So no iteration, just one, right? One. So your solution will be more stable if you have more iteration, then solution will be more stable. Okay. So how do you select the minimum delta t? So this is important. So your solution is more stable if you have more iteration. So minimum iteration or minimum delta t, you can select based on your equation here. So this term you can make it 0. See f0, if f0 you can say 1/4, then this whole term will be 0. Like f0 equal to 1/4. Then 1/4, so it will be 1. 4 multiply 1/4, so it will be 1. So whole term will be 0. So f0 should get less than equal to 1/4. Then your solution is stable. Like this is the minimum criteria. So f0 1/4. So you can get the delta t from here, because f0 equal to alpha delta t by delta x square equal to 1/4. So from here you can get the delta t alpha. So you can calculate the step minimum time step. Okay, so this is the stability criteria we need to consider in this problems. So here if you have 0 1/4, then this is stable. So you can get the alpha delta t by delta x square 1/4. So this is the minimum. You can go less than 1/4, then it will be more stable, like the solution is more accurate. And if you go less than this, then you can see the solution not changing. So his solution is more stable. But if you say delta t equal to 1, delta t like f0 equal to 1, what about the solution? 1, then you can say 2. You can see the variation, huge variation for each solution. So it is not stable. So minimum delta t or iteration we need to consider by considering the stability criteria. look at this one, p plus 1 equal to 2f0, all of this. So you can do the same way, and after simplification you will get like this type of equation. So 1 minus 4f0, 4 beta I f0, this. So here this term somehow make it 0. So 1 minus 4f0, 1 minus f0, only this term, 1 minus 4f0 minus 4 beta I f0. So 1 minus 4f0, 1 plus beta I. So this, if you consider this equal to 1 by 4, then this whole term will be 0. Then from here you can calculate the delta t, the time step. If you know the beta you can calculate HL or H x by, so beta is delta x by k. So you can calculate from here delta t. So that is the minimum time step, and you should consider that or less than that. Then the solution is stable. If you look at this here, this one, so this term somehow make it 0. So 1 minus 2f0 2 plus beta I. So this term, this take it half or less. So half of cancel, so this 0. Are you following me what I am talking about?
Yes.
For this equation here, we want 0 this term, so 1 minus 4f0, 4 4f0 minus 4 by 3 beta I f0. So 1 minus 4 f0 plus 1 beta I by 3. 1 minus 4 f0. 4 f0, so 1 plus beta I by 3. So this means 1 minus 4 f0, 3 minus 3 plus beta by 3. So 4 by 3. So this term, if you say 3 by 4, then cancel. So it is 1. So this term will be 0. Okay. So this is the stability criteria. And stability criteria we want to choose because we want to know the time step. What should be the reasonable time step? So that is the minimum. So you need to go more or less than that time step. or at least that time step. Then your solution is stable. Otherwise, your solution is not stable. So we'll do an example in the next lecture. We have another lecture today.
Doctor,
Yeah.
doctor, you called me and I was having internet issues.
Internet issue?
Yeah, my name is Furqan.
Okay.
Thank you.
Okay. So you have another lecture at 12:30, right? So come at 12:30. Thank you very much for attending.